and what's been going on. Many of them don't know what we do. I also wanted to mention before we get started, so we have a minute or two here. There are some handouts in the back. It's been very hard to publish things in this area in the American Physical Society, and we have finally realized we have to go to preprint servers, and there is a preprint server called Chemical Preprint Server where we've been invited to submit papers, and you should be starting to see papers there fairly soon. The website is there in the back. It shows it. There's also a poster back there, and the address is preprint.chemweb.com, and so I would encourage people to submit papers there and people to start reading them. All right. Okay. Well, the second talk, as I said, is by Mike McCoubry and Fran Tanzella, Paolo Tripodi, and Vittorio Violante. On the SRI-ENEA collaboration to investigate gases in nuclear effects. Now, what you may not know is there's an official program that's going on in Italy, and that's what the ENA is sponsored by the government, and they're working together. Okay, go ahead.
Okay, well, Scott has pretty well covered this. I might say in the ENA cold fusion program, there are kind of two groups operating out of Frascati, and kind of leadership is provided by Vittorio Violante for this part that's cooperating with or working together with SRI. Now, the program thrust on this experimental work is continuing work which was reported on in ICCF 8 is basically studies of excess heat and nuclear products using heavy water electrolysis on Arada-style cathodes. As we mentioned before in my talk, those are bottle cathodes made of palladium bottles filled with palladium black, pumped down, hermetically sealed, put into an electrolysis cell. Deuterium or high deuterium is plated onto the surface of the bottle, diffuses into the inside, and then hydrides the palladium black on the inside. And this other thrust is a continuation of work that was pioneered by Professor Case, which is based upon palladium on carbon catalyst, actually made by United Catalysts, which is now part of Sud-Cadi in Italy. And this is done at elevated temperature, and again, the goal is to measure excess heat in nuclear products. This program has been basically in transition this year. The major thrust of it has been to add to the SRI program the ability to observe reliably very small amounts of helium-3 and to improve their capability of measuring helium-4, plus, as we will talk, production of these cathodes in Italy and working with Sud-Cadi on the catalyst problem. The background for this work, it's important to know, for those who are not familiar with it, the previous work at SRI, which has gone on for 10 or 12 years, has been very accurate calorimetry and the measurement of helium-4. And this is probably their most important run, which is done with an electrolysis cell and a completely hermetically sealed container with a recombiner in it, so there's no gases going off and no chemical energy loss. And this cell was operated for the number of hours indicated, and at one time there were two major bursts of excess heat, or events you might say. The green is actually an empirical expectation fit based upon current density, loading, palladium loading, which McCoubry measures by resistance of the metal, resistivity measurements of the metal, and the other factor that enters into that is the flux of hydrogen, or deuterium in this case, into or out of the cathode. That's solid metal cathode work. Anyway, for the helium, the nuclear product measurements, these excess heat spurts have been integrated, and this is the integral of the excess energy that's coming out. So it's basically megatoules are integrated watts seconds. Okay, so this gas that came out, Mel Miles pretty well established that most of the product helium came out with the electrolysis off gases, and so in this particular case, these gases were collected in this hermetically sealed container, all engineered by Ben Bush, who is, those who know him, is an extremely careful worker, and especially as regards getting things really tight. Also was carried out surrounded by an atmosphere of nitrogen. Anyway, when they, so here's the integrated excess heat expressed in terms of the expected concentration of helium in this container gas, assuming 23.8 MeV per helium atom. And when they first sampled the gas, they did find helium in there, helium-4, at 62% of the amount that explained the integrated excess heat. But about a week later, this value had grown to 69%. These fluctuations represent removing helium, what they used in their sampling, and then making it up from a bottle which contained a little bit of helium that had to be corrected for. Then they temperature cycled this material, this cell, back and forth, running it anodically and cathodically also, so the temperature and electrochemically cycled it. And then they again measured the amount of helium, and they found that it corresponded to 104% with significant error bars, matching the integrated excess heat. So that's a background to their work. The other background I want to show you is published in ITCF 8. They obtained a lot of cathodes were made in Japan. 2 of them were operated in series in Japan, and using the Electrolysis protocol. The same, 2 of them were sent to SRI and were operated at SRI using that same protocol. The current to each of them was the same. The voltage varied for the chemistry in the individual cell. The one was operated in light water in each case, and one in heavy water. This is the one operated in heavy water, leading to about 8 watts of excess power. And the hydrogen one, light hydrogen, is with an experimental error of 0 excess power. So this is the background for the new thrust of the work. The important developments also, though, include a sampling of the gas in the cell that was operated in California. And this work has been published in Fusion Science and Technology last September. And here is the cell, this little bottle containing palladium powder. I might say this palladium powder has a density of the order of 1 to 2 grams per cubic centimeter. So it's mostly vacuum and just a little bit of metal. This powder is punctured, and the gases that were contained, this is long after the experiment has been done, and the gases that were contained were sampled. The sampling, this was done at Pacific Northwest Lab, in Oliver's lab. The sampling, this is the manifold of that was used. Here's the puncturing device. We have various valves, capability of pumping down to very low vacuum, pressure gauge, and that sort of stuff. One thing that happened, there was a problem in the sampling thing. When they opened this valve, they saw no rise in pressure in the pressure gauge. And so they didn't know what to do. So they closed this valve. They had to find out what pressure was there. They pumped out all this vacuum area, They put nitrogen in there. The gauge still did not read. They found that the gauge was set between two different scale settings, and once they found that out, they knew. They corrected it, got good readings, pumped all the stuff out, closed this valve, opened this, and collected their sample. So they collected slightly less than 10% of the gases that came out initially. And this may have affected some of the results which they have. But the most important results are probably not affected, and they will certainly argue that point. I agree with it. The gases that were collected at about 30 millimeters of 30 torr pressure. They actually, first thing, were not pure T2O. They found 75% of the pressure that they collected was water vapor, which for me was a surprise, but shouldn't have been, because palladium black, as you produce it, has oxides on the surface, and the hydrogen that diffuses to the metal forms water. So it's 75% water. So this means that those surfaces were coated with water during heat production. Another important thing that they did was they sectioned the wall of the container of that palladium bottle and they found that the gases contained helium-3. And the wall material, when they outgassed it, also contained helium-3. And they found that the helium-3 was highest in the sections that were collected from the wall closest to the interior of the bottle and lowest at the surface, fitting more or less of a diffusion process. The concept that the way they picture this is that during the period of time that after they ran this cell cathodically, they reversed the polarity and pumped the hydrogen away, and hydrogen-containing tritium apparently diffused outward, and this fits the proposed profile of a tritium diffusing decay for a short period of time, giving that distribution of helium-3 in the wall. The conclusions that the Kukri has made, the gases were analyzed first, as I say, at Pacific Northwest Lab, but then by Clark at McMaster University. They surprisingly discovered this helium-3, and they discovered it was increasing with time, therefore was interpretable by tritium. They took samples in aluminum glass containers and separated the samples for dry gas, hydrogen, and the gas that was contained in the water. And 96% of the tritium was in the water. I guess that's really all I have to say. There's a history of the helium-3 data measurements, which is just shown briefly here, and which may relate to the loss of sample at the time in the collection period, so that's arguable. Anyway, these 2 points, first measurements at Pacific Northwest Lab, were initially listed as 0. One was later changed to a trace. A very low pressure sample to test the system at McMaster University. And it recorded this reading here. If there was any gathering of water in that sample by the input manifold, it could be as low as here. Then the rest of the they at that time is when they collected these aliquots, these are samples of from the water content and the hydrogen content, and independently measured the tritium. This is a measurement of high confidence of Clark's on the tritium content. The measurements actually carried out. The sample was repackaged at this point at McMaster with a pump that did not collect all the water, and as a result, subsequently the amount of tritium found was less than this region here. Anyway, this has been an attempt to model that, and that's basically where the situation stands.
At that time, you made one of the most important discoveries way back in, 91, right?
Before that.
90. That helium-4 does seem to be the dominant byproduct in these anomalous nuclear reactions, and that really changed everything. And he's done a lot of great work.
So you have a code.
What the line?
This has to do with the work at Middle Tennessee State University. I'm working there temporarily, a one-year appointment, teaching at Middle Tennessee State University. And all the authors here are students in my physical chemistry class. And so they have interest in this subject, and we did that for an experiment in the laboratory, and this is some of the results. And some of it is still ongoing, and some of this is preliminary. The reason for interest in the boiling point is in a cell, any kind of cell, but this is the Washington type cell. As you drive this to boiling, of course the electrolyte level drops, and for example, this is a 0.2 molar lithium deuteride, LiOD, and as you boil away, it becomes 0.4, 0.8, and 1.6 mol, eventually it becomes a saturated solution. And in evaluating the excess heat, it's important to know what the boiling point is, and you can calculate it theoretically to a certain point for dilute solutions, but it's not known in the literature. For as we know, in heavy water, the boiling point elevation at higher concentrations, and that was our purpose, is finding what the boiling point would be at higher concentrations. This just shows results of a palladium boron electrode to excess heat in Japan. NHD laboratory, and shows the excess heat. There's two quite large effects here. This is the excess enthalpy per day on this axis. These are the days. We ran this for 70 days, and you see significant excess heat for palladium boron material. And we drove this to the boiling point. And Martin Fleischmann did analysis of the excess heat here. And as you drive to the boiling point, the excess heat goes up. This is up to 25 watts per cubic centimeter of palladium. And at this point, the cell becomes dry, and the excess power continues even a couple hours after the cell is dry, and electrolysis power ceases. There's still a heat after death, it's so-called. And but to calculate this, you need to know how the boiling point changes as the concentration changes, and that was not known in the literature. You can only calculate it theoretically. This shows how you would calculate the boiling point elevation. This is typical physical chemistry textbook. You find it in almost any textbook for the excess, the boiling point elevation. This is the heat of the vaporization of the liquid, in this case water. This is the temperature of the pure liquid. This is the temperature for the mixture, and so it depends on the heat of vaporization and so on. It does not depend on the salt. Theoretically, it does not depend on what salt you're studying. At least theoretically, just the mole fraction of the water or the heavy water. And but you need to calculate the mole fraction, and you do that easily from the molality of the solution. So you can theoretically calculate the boiling point elevation, but that equation only works for dilute solution because the approximations made in deriving the equation. This shows some theoretical calculations of boiling point elevation at different molal concentrations. Molal, of course, is moles of solute per kilogram of solvent, and this is the boiling point calculated for water and heavy water. Heavy water is actually a little bit greater, and this is theoretically calculated down to 10 molal, which, of course, the equation wouldn't hold there, but you can see that the heavy water is a little bit higher in value, calculated theoretical value. We've actually measured this in the laboratory, at least we're starting to, with the regular light water. This is what we measured experimentally. This is what we calculate, and you see some large differences, which is not surprising. And only for dilute solutions is very close. In heavy water, we just started on this. 1 mol. This is kind of surprising. We got that large value. We have to go back and check it, so we have a question mark. We still need to 3 molal, and not too far off the theory actually for 3 and 4 molal. With regular water, you can go to 7.31 molal before it saturates. It looks like it starts to saturate around 4 molal, so it's not as soluble in heavy water apparently as in light water. So these are some of the early results on the experiments of what we measured in the laboratory, the boiling point elevation in LIOB in heavy water. This shows how the calculated and theoretical values compare. The red is the experimental values, the line and the blue circles are the calculated value, the theoretical values is the blue dots, and the line is the best fit to those theoretical values. And this is regular water here, and what we measure here follows fairly close, but at high concentrations, the boiling point elevation is less than what you calculate theoretically for LIOH in regular water. If you do this with heavy water, and this has never been done, actually it's never been done in light water. We have not found literature results for either light water or heavy water for LIOH and H2O or LIOD and D2O, so this is all new as far as the literature goes. Again, the blue dots in heavy water are the calculated theoretical values, and the red is what we're starting to measure in the heavy water. And again, that's a little bit surprising that it's a little bit higher than you would expect. Whether that's real or not, we're going to go back and check it. But at higher concentration, it comes back and follows the line reasonably well. At these concentrations, you really don't know whether it's going to fit the theory or going to be higher or lower. This is kind of surprising. In this case, it came out pretty close. Because the theory only holds for this region down in here up to about less than 0.5 molal, actually even less, probably 0.1. So it could go either way experimentally. But in this case, it did follow the theory fairly well up at the higher concentrations. Just to show you the trends you can get, theoretically, the boiling point elevation does not depend on what salt you use. It only depends on the mole fraction of the H2O or D2O. For hydroxides, with our new results added here, for these concentrations, we find KOH is much larger than sodium hydroxide, and that's much larger than LiOH. And so theoretically, these would all be the same. And at 5 molality, the theoretical value would be 4.78. So you see these all differ. But if you go to chlorides, then the lithium salt is the greatest boiling point elevation experimentally, then sodium and then potassium. So you have no way of knowing how this is going to turn out because it does not follow the theory of these high concentrations. Iodized, the sodium is the biggest boiling point elevation, then potassium, and then lithium. And then in nitrates, sodium is first, then lithium, and then potassium. So at least for the hydroxides, lithium is the lowest effect of the boiling point elevation of the hydroxide. Lithium gives you the smallest effect in the case of hydroxide. Now, the interest in this, of course, is the excess heat effect becomes larger at higher temperatures. There's positive feedback. If you can start getting excess heat, if you can push the temperature up, you get a bigger effect. And in regular water, you're limited by the boiling point of the water. So the idea, can we push the temperature up even higher than the regular boiling point of water by going to other salts? And this shows from the international critical tables, you can get quite high boiling point elevations for certain salts. Sodium nitrate is quite soluble in water. You can get a boiling point up to 119.6 degrees. The boiling point elevation is given there. Lithium bromide, also very soluble. You can get up to 144.8. These are experimental values that have been measured. For lithium chloride, very soluble, you can get up to 165.7 degrees Celsius, both push the boiling point. And with the hydroxide, you can really go up to 176 for sodium hydroxide, and for potassium hydroxide in water, you can push it up to 236 boiling point elevation, or up to 336 operating temperature in a concentrated KOH H2O solution. So this is what I think is needed in the future is excess enthalpy studies in palladium, heavy water, and KOD, and push it up to very high temperatures and see if you can continue to get this positive feedback and get larger effects as you push the temperature up. Sort of related to the hydroxide work that Talbot Chubb has pointed to, and that's also a direction we could go. We could look at the excess heat effects in molten hydroxide, lithium hydroxide, sodium hydroxide, up to 210. You have this key equilibrium with water. You you add oxide on, you push it back this way. These are probably the cathodic reaction, and this cathodic reaction with low deuterium into the palladium, and this is anodic reaction. And so this is another area in molten hydroxides at high temperatures. Would we get large excess heat effects? So I think the future we should look at palladium in heavy water with KOH, with boils at high temperature, or maybe going to molten salts. That's what I suggest as future work, and I would like to do it, but I need to find a place to do it. Thank you.
Got time for a couple of questions. Yes, Paul.
I'll make a comment. Potassium hydroxide is always bought with 10 or 12, 10 to 13% water in it.
Right, yes.
And Aldridge does offer to make potassium deuteroxide with B2O in it,
Right.
but they want $5,000 for a kilogram.
Right.
So maybe it would be nice if somebody could provide that.
Yeah.
And that would make this sort of thing
Yeah.
useful.
It would certainly be an interesting experiment to do. And the advantage of KOD in heavy water would be that you could start off at low temperatures and load the palladium. And then when you start getting excess heat, you can push it well past the regular boiling point of water, away to very high temperatures, and continue measuring excess heat.
Any other questions? Okay, we'll move on.
One right there.
Oh, sorry, I'm sorry. Yes, go ahead.
Could you point out what's the relevance of this addition of boiling point to both species?
Well, we get larger effects at higher temperatures. And in regular water, it's going to boil around 100, just a little bit over that. And so if we get salts that push the boiling point up even a lot higher, we can go to higher temperatures and get bigger effects. Right now, we're limited by the boiling point of the solution. But in these other concentrated salt solutions, we can go much higher in temperature and continue to see even larger effects. So at least that's what is predicted. Because the positive feedback, the excess heat effect increases as you increase the temperature.
There was a long time ago, they got this non-linear effect, created quite a stir with the quote, heat after death, where the water just boiled right away. Very spectacular. Okay, well, the next talk is going to be given by Andre Lipson. Lipson, Rosetsky, Style, and Miley. And they're all involved with this excellent effort, the LENR laboratory, which is at the University of Illinois. And George Miley is to be commended for bringing wonderful scientists like Andre Lipson to the United States and getting them involved. I might point out that Andre gave me a couple of papers that are in the American Institute of Physics and Russian Journal from 1990, where they did cavitation and they saw neutrons, but it was off of a titanium surface. So 10 years ago, they were seeing nuclear byproducts of this kind of thing. Bubble sheet. Okay.
Okay. As you can see later today, so this work is only part of broader force on study of lattice-induced nuclear reactions that were carried out in the low-energy nuclear reaction group. This group was created by Professor Miley in the University of Illinois. So, in this presentation, we studied nuclear emissions that accompany electrolysis in the light water, the electrolyte. All details concerning the electrolysis process and multi-layer thin film will be done in our other presentations today. So this was a collaborative work with the Electric Physics Institute of Russian Academy of Science. detection, we use here solid-state detectors such as CR39 plastic detectors that were directly attached to metal layer. And as a background, we used the same detectors that were immersed in electrolyte or attached to opposite side with no metal coating. In special experiments to determine, identify type and energy of emitted particles, we used copper shielding of these detectors. After exposure detectors were each, it was standard procedure and investigated with optic microscope. We used calibrated detectors, so they were calibrated for alphas and for protons separated using cyclotron facility for high energy alphas and Van de Graaff accelerator for protons. This is typical calibration curve of alphas. So to obtain points until 8 MeV, we use alpha sources and then cyclotron. The tracks, that's the typical tracks from cyclotron from 12 MeV particles. After etching of detectors with modification. So this something like 7 micron diameter of track. This is on the graph proton calibration. It is possible to see that we have overlapping of proton and alpha tracks, starting from 6 micron to 10 micron track diameters. And to separate them, we use metal screens to separate protons. So for X-ray detection, we use In-Situ. We use the thermoluminescent detectors from lithium chloride and alumina. Alumina detector is more sensitive. One order of magnitude more sensitive than lithium chloride, and they have high enough initial background. Yeah, 10 millirem. Our experimental results. We, in our spectra, we obtained 2 significant peaks at 7 and 6 micron. This is experimental spectra. So, as one can see in foreground, we can see only these peaks. And it is important that at track diameter less than 7.5 micron, we don't see such tracks in the background. So after, for shielded detectors, there is another step. So these peaks disappear in this area and shifted to upper limit of yield of soft X-ray quantity, something less than 5 quantity per second per square centimeter, but reproducibility not so good. So we concentrate on charged particle track. So as I said, in accordance with calibration, tracks with diameter 7 microns could be 13.5 approximately alphas or 1.25 protons, and tracks with 6 micron diameter, maybe 29 MeV alphas or 1.7 MeV protons. And note that used 25 micron copper shielding totally absorbs all alphas with energy less than 9 MeV and protons with energy less than 2.4 MeV. In this connection, here we can see total differences between foreground and background runs for shielded and open detector. So this peak, something 13.5 MeV alpha. After shielding, in accordance with alpha particle stopping ranges and stopping power, we can see several splitting of this peak to at least three peaks in energy band from 10.7 until 16 MeV. And in the range of normal activity of alpha activity of radiating background, nothing interesting. So, because these alpha particles, it's well known, cannot be absorbed in natural background because the last isotopes of radon Syria have energy 7.8 MeV, and then nothing alphas in background can be seen. So for protons, it's another thing. We can see that the peak that we saw at 6 micron diameter will be protons because they're completely absorbed in 25 micron copper. And for copper covered detectors, we see here nothing. So we see simultaneously protons and alphas. So in accordance with efficiency, the intensity of proton emission, something like that, and alpha emission, something like 1 particle per hour. But proton emission is more intensive, 5 or 6 times more intense. Okay, our conclusion that during the electrolysis of palladium nickel thin films, we see alphas with energy something like 30 MeV and protons with energy 1.7 MeV. I need to say that excessive production that will be reported later not always correlate with charged particles emission. So more charged particles we can see when metallic coating destroyed completely. And the upper limit of X-ray emission rate during electrolysis doesn't exceed several quantities. So it's proved that in this experiment that we carried out, no massive nuclear reactions were observed.
7.
Could you say anything, if you have a 13 MeV output once in a while, is that assuming the output is produced right at the surface of the...
Well, and H. Lipson, GH Blue, and GH Miles.
Yeah, what's your opinion?
I did before.
Yeah, actually, a couple hours later.
Yeah, that's right. That's right. Oh, yeah. Okay.
Okay, my talk is about the resistance measurement of spattered trading film to electrolysis. This work is performed where you see the LENR group of USA. And first I'm going to give you an outline of this talk. We're going to go through the purpose and also first we'll do some background information and experiment setup and so on, and we will address results the later part. So the background information is we have a general, it's sort of like a general so-called resistance loading curve for plating hydrogen system. And let's say the resistance is product relation. The R naught is the resistance of without any loading, because that's the initial resistance. And there's a general relation between the ratio and the loading. Okay, that's hydrogen per plating. And for different isotopes, we have different curve. Okay. Let's try different, but the curve, I mean, the shape of the curve is similar actually. So you may wonder what object will measure the resistance. I mean, how is it close to with nuclear stuff? Well, so let me explain to you actually. First I want to say is that silicon hydrogen. Because we tend to ask the coefficient is usually related to the loading ratio. You want to get a coefficient, it has to happen at some sort of high load. And we always want to say to which extent are those film loaded. We also want to, I mean, this sort of like help us to understand the phenomenon behind, I mean, the mechanism behind the coefficient phenomenon. Because I mean, there seems to be a general consensus on the coefficient can only happen if you have some sort of like a non-equilibrium mechanism. Because in equilibrium, you have only potential, extra potential a few volts. You cannot generate any sort of like stuff. So we want, actually, you can say you want a physics. So we know we have to look at the non-equilibrium. So that's our reason. Okay. We also want to pave the way for similar diagnostic technique and temperature profiling. Because we seem to us, I mean, the coefficient happens to some hotspot in the cervix. So we want to say it's only a hotspot of that. So we also want some techniques similar to this. So let me show you the experimental setup. So actually, there have been lots of like previous layers for wired samples, but for since the first time of best of our knowledge. Okay, but the problem is like during experiment we have electrolyte. I mean, which contacts with the electricity. So you're wondering how can you tell me the resistance of the symptoms apart from the resistance of the electrolyte? Actually. We just cover it with epoxy on the surface. Actually, in this case, we have the alumina substrate covered by nickel thin film, and this part is epoxy. We make some Indian dots here by vacuum soldering. And we cover this part with toxic, some clear toxic, and you can purchase in ordinary hardware store. And then we have the AC measurement here. And you may wonder why we just use a 2-point probe. I mean, they say you would have to use a 4-point probe. Actually, it's not an issue here. That means the electrical contact is good in this case for metal. In fact, while they're dealing with the superconductor, while they're dealing with the semiconductor, so we don't have to bother with that. And this is the close-up on the electrode. This is a spattered metal film on top on aluminum substrate, and this is the Indian solder. I can say there are actually and this is covered up. This is the electrode covered by these are epoxy. And here we also say the yellow bit actually is thermistor. We want to say the two-layer profile, so that's something I didn't put in the slide. So we have basically say initially we'll actually sort of turn on the electricity somewhere here, and the horizontal scale actually is 10. The horizontal electricity is time. You can say somewhere here is like 12 by something second. Okay. And this is usually this. You can see generally you won't turn on the electricity. This is increased rapidly. And actually the loads over only a matter of half an hour. It's much faster compared to wire loading. So I would spend more. That's the case. So basically, we have the observation in that. Basically, we have similar, the resistance versus loading behavior, and behavior similar to the bulk gradient. The difference is like we have much faster loading. Ordinary loading takes like, for wire, okay, we have like days or weeks actually, but in the case of film, we only have half an hour. Let me just explain to you why this case. We get, we don't know for sure, but we get sort of guess, much faster diffusion with everything on the green boundary. Just, when you start something on a substrate, it's sort of like, the green, the size of the crystal, it's a polycrystal metal film. So the size of the crystal actually is very small. It's much smaller than ordinary you can obtain for a bulk material. Because it's not a crystal, it's not really a active process. It's just sputtering. And the substrate in that case is kept at the room temperature, so you don't have the nice gross temperature for extrusion crystal size. So that's one reason. Second reason is we guess assuming actually it's very much higher current density actually. In case of thin film, because of the cross section is much smaller, it's very thin. The thickness of the thin film is on order of 1 micron, actually less than that. So you have much higher current density. Like thin film, okay. The current actually is on the order, on the order of 1 ampere actually. So because of the thing, the cross section of thin much is very small compared to the wire. So the current is the order of the magnitude higher than the Lipson wire. So here is our conclusion. This seems to be the first successful menu of thin film during electrolysis. We found that the thin film can really be quite highly loaded. The ratio are actually somewhere at 0.8 or so. Okay, 0.8. Actually, it may not be that high. May not be high enough for like smaller than 0.5%, so 0.5, okay. But actually, we sort of like, not sure. I think we have like 1 minute or so.
Yeah, but you still have to keep going.
Okay. So we also like similar techniques can be used to characterize temperature profiling and some other. Also we sort of put the small nuclear detector on top of the surface and say what happens. And finally, if you have any question, you can contact me. This is good. And we acknowledge the support by.
We actually still have a minute before it talks over right now.
Yes.
Yep, Peter.
So the bottom line from your measurement is you got a loading to be about size like 0.85, 0.87 or something.
I guess it means just actually maybe less than 0.85. It's just a matter of like.
Right, and we put a current there and deposit palladium metal in the presence of evolving deuterium gas. And then we're getting this cauliflower-like structure. It's black, it's mossy, it has a lot of very high surface area. And because of the structure, we have non-uniform distribution in the current density and the overpotential. Because it's a very large surface area, we get rapid absorption of the deuterium into the metal lattice. And we also have achieved very high deuterium palladium loading. We measured deuterium palladium loading greater than 1. And we achieve these loadings within seconds. Now, we have not done any calorimetry of the palladium deuterium system ourselves, but we do measure the temperature of the cathode and the solution temperature, and we always have found that the temperature of the electrode is 2 to 3 degrees hotter than that of the solution, indicating to us that the heat source is the electrode and not dual heating. While we have not done calorimetry, Mel Miles at Naval Air Warfare Center Weapons Division has done so. He has run 3 cells, and he has achieved excess power every time. His excess power ranges anywhere from 100 to 400 milliwatts. What we have done is we have done infrared imaging of the electrodes during the co-deposition process. And in these experiments, we take a nickel mesh electrode, put it very close to the cell wall, and have using an IR camera. And here, if you look perpendicularly, you see the distribution of the hot spots. They are a very short time duration. You feel that in parallel, you see the temperature gradient. The temperature gradient is very steep, telling us that the heat source is very intense and that it is located close to the contact surface. In one instance, we actually did get catastrophic melting. We had filled the cell before we left for the day. And the next morning when we came in, the cell content had boiled away. And instead of getting the black, mossy palladium, we saw these silvery streaks of palladium along the cell wall. And when we took samples and sent them away for analysis, the metallurgist told us that the only time he had seen formations of this type was when metal had melted underwater, and palladium melted at 1,552 degrees C. Now, the infrared results indicate to us, or suggest to us, that the events we are seeing are explosive in nature. And if they're explosive in nature, you should see pressure waves. And the easiest way to detect pressure waves is to deposit the palladium and deuterium on a substrate that is pressure sensitive, such as a piezoelectric crystal. And that's exactly what we've done here. We have our piezoelectric substrate, the lead zirconium titanate disc of this radius and that thickness. Here's the source of it. And on it we have our silver electrode onto which we plate our palladium. And the idea is that when you get a heat source, you should get a pressure wave that would hit the piezoelectric crystal, and you would see a constriction of the crystal. And this would show up as a voltage response. And once the crystal relaxes and expands again, you'll see a relaxation curve. And this is a very reversible system, and the areas of these curves should be approximately the same. So here we set up our experiment. We have a Faraday cage. Inside it we have our electrochemical cell. This is our counter electrode for platinum wire. This is our piezoelectric crystal. Here's the silver film exposed to the solution. The rest of the surface of the crystal we have covered with an insulating material. We have a potential step to control the voltage between, or the current between the counter electrode and the silver on the piezoelectric crystal. And then we have the lead from the piezoelectric crystal going to oscilloscope where we measure the voltage difference. And that voltage difference would be proportional to the constriction and expansion of the crystal. And here we see typical results. This is for low current cells, where the current is less than 1 milliamp. This is the result for higher current, between 4 and 5 milliamps, and this is for zero current. And initially, we don't see anything going on, just some background noise. But eventually we get to the point where we have enough palladium on the silver where we start seeing these spikes. Here, at higher current, we see a lot more activity. At this point, we have evolving deuterium gas, which is going to be contributing to some of these features that we see. And interestingly enough, when you turn the current off, you still see these events occurring. And these events continue on for as long as 3 to 5 days after you turn the cell current off. If we look closely at this example here we see a pressure gradient, which has caused constriction of the crystal. And as I said before, when the crystal relaxes back, the area of these two peaks should be the same. And you can clearly see that this area of this peak is going to be greater than this one. So there's another source contributing to that area, that peak area. And if you think about it, if you have a heat source causing a pressure gradient, you're also going to have a temperature increase. And that temperature increase is going to cause the crystal to expand. And so we have both of these features contributing to this area. After we have conducted these experiments, we have taken the crystal, put it into a light-tight envelope. We put a membrane, very thin membrane, over the crystal and taped it in place. And then on top of that, we put photographic film. And we allow it to be exposed to photographic film for 3 to 5 days. And afterwards, we have the film develop. You can see here that we're getting radiation of some sort being emitted from the dark spot here. You can see the outline of the piezoelectric crystal and see these distinct spots occurring. We don't know quite yet what radiation we're getting. We don't know if it's regular light. We don't know if it's X-rays or what. We're doing ongoing experiments to determine what the radiation is. Another thing we're working on is, can we quantitate the results we obtain with our piezoelectric crystal? And in particular, can we say something about the location of the reaction site as well as the strength of the heat source? And this is the model we're looking at. Here's our piezoelectric crystal. We're assuming that our heat source has a spherical volume of radius A. And we have our heat source which radiates out, and you get this thermal wave function of R. And this is described by this equation shown here, where the temperature at any time R or any time T is dependent upon the magnitude of the heat source. K here is the heat conductivity of the palladium deuterium material. A, of course, is the radius of the initial sphere. And if you take as a limiting case A goes to 0 in the case of the point source, this equation reduces down to this form here. Now, actual quantitative evaluation is going to be very difficult. You have to do a transducer calibration. We also have to do a temperature distribution, and the best way we can do that is by the IR imaging. So we have to redesign the experiment in order to do the plating on the piezoelectric crystal at the same time doing the IR imaging to get those, to see where those spots are occurring. And we also make a number of assumptions. We have to make assumptions about the morphology of the codeposited film, as well as the heat transfer and the dissipation of that heat into the liquid phase. And clearly, the best chance that we have of getting any quantitative evaluation would be when we have a zero cell current, because we totally simplify things. But we don't have evolving deuterium gas, and it makes things a lot simpler. And again, that work is still ongoing. So in conclusion, characteristic features of the stadium experience system are that first off, you get immediate initiation of the question concept. We don't have to charge our electrodes for weeks as other folks have to do with their rods and wires. Every time it works, there's greater producibility and repeatability. We do see excess enthalpy generation at low cell currents, which is, again, opposite of what is observed with the rods and the wires. And we still see events at zero cell currents. And these last two features indicate to us that you're going to have to revise our concept, our theories on the nature of this phenomenon. We'd like to thank Dr. Frank Gordon for his support and Greg Anderson for his technical expertise in setting up these experiments. And again, if you have any questions, you can contact me at bosst@baywar.navy.mil. My fax number again, area code 619-553-2836. Thank you.
Okay. Go ahead. DD going to helium-4 cold fusion implications drawn from helium-4 plus gamma going to DD. And this is information where you can contact me. I also work at the Naval Research Laboratory. I'm doing this under the auspices of Research Systems Incorporated. So I'm going to start by looking at the importance of electromagnetic interactions. And the problem, the traditional problem is obstacles to be overcome in getting outside the box. That is, people have a particular way of looking at fusion reactions. They don't look very often at this reaction. And there actually has been some confusion about this that I've heard at ICCF meetings and elsewhere. And I'm going to add, and then I'm going to use a little bit of motivational physics for getting outside the box, and some comments about reaction theory and how it relates to missing gamma rays. The upshot is there is no missing gamma rays. It doesn't have to be. Okay. So what I've done here. Schematically, some of you have seen this before. I'm going to talk about being outside the box, which is what we expect might be true, but it's unconventional. Some people, like Bob Park, would refer to this as true science, but I'd call Bob Park's true science true science. Inside the box is what we know is true, that is conventional physics. Now, in fact, in this diagram I show what one knows about conventional fusion reactions. I've shown a neutron and a proton and proton-neutron pairs coming together, forming what looks like the excited state of a helium-4 nucleus. Now, when you're near the top of the barrier of the Coulomb potential for all different speeds, you can do a tunneling type procedure that ignores a lot of the details associated with the Coulomb barrier. And so you can split proton-neutron pairs and form either helium-3 plus a neutron or tritium plus a proton. Now notice though, there is another reaction where you get helium-4. And this one involves really important electromagnetic coupling. Traditionally, there's a gamma ray